A couple other people hopefully get into class here shortly. So before we get into our lesson for today, I want to talk about the last few weeks here. This week we will be covering chapter 3. Mostly it will be like me getting through the lessons and then showing some examples tomorrow. There won't be an activity to go along with this chapter, simply because I'm just trying to make sure we cover it and that we've seen it and we have an idea of what it is. We will not be covering chapter 12 in class. I will have materials for chapter 12 on Canvas, but I will not be using any live class sessions to go over chapter 12. This is because it was kind of what was suggested based on the amount of time I have left and the fact that I want to look at some practice, like free response questions and things for the AP exam, before the exam happens. That the suggestion was to cover chapter 3 and skip chapter 12. And this is primarily because chapter 12 only makes up about 2 to 5% of the exam. It's a very small portion of the exam that chapter 12 might come into play, and we're taking the gamble that it doesn't show up at all, right? Because that's a possibility. So that's kind of the reasoning behind that. Yeah. So we'll do chapter 3, and then next week we'll get into looking at free response questions from previous exams. We'll look at how they're answered, how the scoring rubrics look, so you get an idea of how like people who grade these things, what they're looking for as you create your responses. And specifically, we'll actually be looking at some of the problems from the first administration of the AP exam this year, because they have a set of questions that have been released already from the exam that happened last week. So we'll be taking a look at those to kind of help us get a little bit more prepared. Also, there will only be one other assessment for this class. I've decided to only do a multiple choice assessment for the last 2 chapters that we've covered. So there'll be a single multiple choice assessment covering chapters 11 and chapters 3. Probably going to be like 15 questions instead of 10 questions, but that will be it. There will not be a free response question assessment. It will just be one more multiple choice assessment that, again, you'll get unlimited attempts on and all that fun stuff. And that will be essentially the last assignment that will be assigned this year, because there won't be any other activities, no other classwork kind of things. It's all going to be review, right? So that's how the year will wrap up. You know, the last week of school for most of you as seniors will be the week of the AP exam, right? June 10th, that's a Thursday. And then the following Thursday, you guys graduate. So it'll be all awesome. Right, so that's the idea for the last few weeks. We really only have like 3 weeks left. That's about it. We're getting to the very end. Is there any questions about the plan for the last few weeks here? All right. Then with that, we're going to start our lesson. And today we're going to get through all of section 3.1 and part of section 3.2. There are only 2 sections in chapter 3. Once we finish what's in section 3.2 tomorrow, we'll look at examples and how to use these things that are probably not going to make a lot of sense today. So I apologize for that, but we'll get there. So there we go. There, come on, go away. There we go. Excellent, here we go. So here we have chapter 3, describing relationships. We're going to be looking at scatter plots and correlation for section 3.1. Scatter plots have to do with, they're kind of like the two-way table of quantitative data. All right. Think of it as like a two-way dot plot is what a scatter plot kind of looks like. So we'll get into those and then how to interpret those. Come on, clicky. All right, here we go. So here's what we're going to be working on with section 3.1. We need to identify explanatory and response variables in situations where one variable helps to explain or influence the other. We need to make a scatter plot to display the relationship between two quantitative variables. We want to be able to describe the direction, form, and strength of a relationship displayed in a scatter plot, and identify outliers as a scatter plot. In a scatter plot. Interpret the correlation, understand the basic properties of correlation, including how the correlation is influenced by others or outliers, and use technology to calculate correlation. We also want to be able to explain why association does not imply causation. That's kind of an important deal. First, explanatory and response variables. Most statistical studies examine data on more than one variable. In many of these settings, the two variables play different roles. We can have a response variable, which measures an outcome of a study. It's the thing that we're collecting data on, whatever value that might be. An explanatory variable may help explain or influence changes in a response variable. So we have response and explanatory variables. Note, in many studies, the goal is to show that changes in one or more explanatory variables actually cause changes in a response variable. However, other explanatory response relationships don't involve direct causation. Does anyone need a moment to write anything down from this screen? And displaying relationships, scatter plots. A scatter plot shows the relationship between two quantitative variables measured on the same individuals. The values of one variable appear on the horizontal axis, and the values of the other variable appear on the vertical axis. Each individual in the data appears as a point on the graph. We'll see examples of these today. When we make a scatter plot, we first need to decide which variable should go on each axis. This is essentially done for us, as the explanatory variable must go on the x-axis, meaning that the response variable is on the y-axis. Number two, you need to label and scale your axes. You should, if you're drawing your own scatter plot, you must clearly label your axes, which one is the explanatory, which one is the response, whatever those actually are in context, and then scale your axes. Right? That means that your horizontal axis should be evenly spaced between the possible values. Okay, you cannot jump different amounts between hash marks. You can go by 5s, 5, 10, 15, 20, 25, 30. You cannot go 5, 10, 30, 50, 75. Even if those are just the values being used, that is not a proper scaling. Please make sure you have equal increments between hash marks on your horizontal and vertical axis. They do not need to use the same scale, but they must be consistent. Lastly, you plot your individual data values, essentially the same way you would plot a coordinate on a XY plane. To describe a scatter plot, we're going to follow the basic strategy of data analysis from chapters 1 and 2. Look for patterns and important departures from those patterns. When you're examining a scatter plot, as in any graph of data, look for the overall pattern and for striking departures from that pattern. You can describe the overall pattern of a scatter plot by the direction, form, and strength of the relationship. An important kind of departure is an outlier, which hopefully we're familiar with at this point. An individual value that falls outside the overall pattern of the relationship. So the key things is when we're describing and examining a scatter plot, we want to describe direction, form, and strength. And we'll see examples of what that is shortly. Two variables have a positive association when above average values of one tend to accompany above average values of the other, and when below average values also tend to occur together. Two variables have a negative association when above average values of one tend to accompany below average values of the other. So essentially it's a positive association if as one increases, the other increases. Negative association if as one increases, the other decreases. All right. Here is an example scatter plot comparing percent taking SAT in a given state and the mean math score of that state. We're going to describe the scatter plot. So there is a moderately strong negative curved relationship between the percent of students in a state who take the SAT and the mean SAT math score. Further, there are two distinct clusters of states and two possible outliers that fall outside the overall pattern. And we have the strength of the association is moderately strong. It is negative because as we go from left to right, we're decreasing. And it is curved. If we look at the pattern of our dots, it's slightly curved. It doesn't really follow a linear pattern. It follows a curve. And we see our two distinct clusters. And we have an outlier over here and a possible outlier, I think, over here. Okay. And so this is the description of the scatter plot. Okay. Here's another scatter plot comparing points per game versus wins. This is from a set of data comparing points per games and wins for football teams in the SEC, which is a NCAA division. All right. And this is a comparison, points per game and wins. The direction. In general, it appears that teams that score more points per game have more wins, and teams that score fewer points per game have fewer wins. We say that there is a positive association between points per game and wins. And that's because as points per game increase, wins increase. Form. There seems to be a linear pattern in the graph. That is, the overall pattern follows a straight line. Okay, this is not curved. This is linear. And our strength. Because the points do not vary much from the linear pattern, the relationship is fairly strong. If we draw like a best fit line through this scatter plot, a lot of the points are going to be close to that line. That's a strong association. There do not appear to be any values that depart from the linear pattern, so there are no outliers. Is there any questions, or is there anything I can clarify about describing a scatter plot? And so that brings us to measuring linear association, which is correlation. A scatter plot displays the strength, direction, and form of the relationship between two quantitative variables. Linear relationships are important because a straight line is a simple pattern that is quite common. Unfortunately, our eyes are not good judges of how strong a linear relationship is. The correlation R measures the direction and strength of the linear relationship between two quantitative variables. So we have a new statistic here, and that is R. All right. R is always a number between -1 and 1. R greater than 0, meaning R is positive, indicates a positive association. Which again, meaning as one increases, the other increases. R being less than 0 indicates a negative association, which meaning as one increases, the other decreases. Values of R near 0 indicate a very weak linear relationship. Which essentially means the scatter plot is more scattered. The strength of the linear relationship increases as R moves away from 0 towards -1 or 1. The extreme values R equaling -1 and R equaling 1 occur only in the case of a perfect linear relationship, which would mean all of your points in your scatter plot lie exactly on a line, which basically doesn't happen. Does anyone need a moment to write anything down from this screen? So here we have some examples of different scatter plots and the correlation R that goes with them. The first one here is R equaling 0. It's basically that the association is incredibly weak. This is just a big scattering of points, right? The line of best fit is probably just a straight horizontal line. We have our correlation R equaling -0.3, so there's a slight negative correlation or negative association, meaning that our line of best fit is going to be slightly downward. As our values in X increase, the values in Y decrease. We have R equaling 0.5. That is like a mild association here. The strength of the association is kind of not weak, but it's not strong. And that's a slight increase, slight positive association. We have R equaling -0.7, so we have a stronger association now. Right, and the line is pointed a little bit more downward. And again, we move along to 0.9, an even stronger association, positive association. And our line is obviously increasing from left to right. -0.99, our points are even more closely clustered to a line. Right, a lot of the points will be on our line. And that's a very strong negative association. So the positive and negative isn't connotating like a good or a bad thing. It's just saying whether or not things are increasing as X increases or things are decreasing as X increases. Is there anything I can clarify about our correlation here? So calculating correlation. The formula for R is a bit complex. It helps us see what correlation is, but in practice, you should use your calculator or software to find R. So here's how to calculate the correlation R. Suppose that we have data on variables X and Y for n individuals. The values for the first individual are X1 and Y1, similar to coordinates. The values of the second individual are X2 and Y2, and so on. The means and standard deviations of the two variables are X bar and S sub X, the X values and Y bar and S sub Y for the Y values. R is equal to 1 over n minus 1 times the sum of the product of essentially the standardized X and Y coordinates. That's the best way I can put that into words. All right, so we essentially have the first X value minus the mean of X divided by the standard deviation of X times second Y value, or the first Y value, minus the mean of Y divided by the standard deviation of Y. This formula should look somewhat familiar. It's essentially the same formula we use when we standardize a score. Right? Our observation minus the mean divided by standard deviation. Except now we're multiplying those two things and doing all this craziness, okay? Your calculator will find this for you. Please don't try to do this by hand. That will take a long time. There's several ways to get this on your calculator. Once you have input your values for X and for your explanatory variable and your response variable in your calculator, which you can do by going to Stat, edit your list. I've already got values in here for L1 and L2 based on the football scores example that we previously talked about. All right, and so we have list 1 is our explanatory variable X value. List 2 is our response variable. So in the example, the explanatory variable was points per game. Response was number of wins. And so we have this already in the list. If I go to Stat and calculate, I want a linear regression. This will give me values that I want. There are 3 linear regression commands in your calculator. The one that we want to use will be the second one. So this one, not correct. Don't use this one. Keep going. We want this one, the 8th option, lin reg a plus bx. The reason for this comes up in the next section. All right. Our X list is L1, Y list is L2. We don't care about the frequency list. We're going to store the regression equation because it's going to come up with the best fit line based on these coordinates. All right, so I need to store that somewhere so I can use it later. All right, so I'll go to vars, yvars, function, and select y1. So it's going to save it in my graphing calculator as the y1 equation. And then go to calculate. All right. And here's R, 0.9358669, blah, 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 blah. That's going to be way faster than trying to calculate this silliness by hand. Much less room for error. Plus, you get more things that we will be able to use in other places. All right, so please use your calculator. Don't do this by hand. So facts about correlation. How correlation behaves is more important than the details of the formula. Here are some important facts about R. Correlation makes no distinction between explanatory and response variables, meaning you need to know which one is which. R does not change when we change the units of measurement for X, Y, or both, meaning if we transform X and Y in some transformation, R's should not change. The associations should be the same. The correlation R itself has no unit of measurement. It's just a number. Some cautions. Correlation requires that both variables be quantitative. We cannot do this with a quantitative and categorical variable. Correlation does not describe curved relationships between variables, no matter how strong the relationship is. Not how it works. This variable R only has to do with linear relationships. Correlation is not resistant. R is strongly affected by a few outlying observations. This is not resistant to outliers. So if we have outliers, those will have a drastic effect on R. This is because R is calculated based on mean and standard deviation. Neither of those values are resistant to outliers. Right. And lastly, correlation is not a complete summary of 2 variable data. It's just one measurement. Is there anything I can clarify here? Any questions? So we'll see some examples here. A few different graphs. For each graph, we're going to estimate the correlation R and interpret it in context. On our first one here, we have boats registered in Florida versus manatees killed by boats. This has a positive association, is relatively strong, it's pretty linear, right? And so R is going to be positive, it's greater than 0 because we have a positive association. And it's probably around like 0.8. Right? A lot of our points are very close to the line of best fit if we were to draw one. And in context, that means the more boats that are registered, unfortunately, the more manatees that are killed by the boats. This one, we have storms predicted versus storms observed. This, if we exclude the one outlier there, probably has a very, very weak association. These are all just kind of clustered here together. We might have a slight positive association here, maybe like through here. This point's going to pull it up a little bit. So we're probably looking at an association of like 0.3. It's going to be positive, but weak. Okay, so there's a small association between the storms predicted and storms observed, but it's not very strong. We've got healing rate of limb 1 versus healing rate of limb 2. This is pretty scattered. The more scattered this is, the less close these things will be to a linear, like a line of best fit, the smaller the value of R is. Right? This might be like a teeny tiny positive, but most likely it's about 0. Right? There's really no association between these two things. They're probably independent, right, if we want to take it that far. Okay. Meaning, knowing how fast one limb heals doesn't really tell us anything about how another limb heals. And then we have this mess of points, last year's percent return versus this year's percent return. If anything, this might have a slight negative association. As we can see, we're kind of going downwards here, but that the correlation R is going to be pretty small because these points are very spread out. So again, knowing last year's percent return doesn't really tell us much about this year's percent return. And that's the basics for our scatter plots and correlation. Section 3.2 goes more into using these things. The last part that I want to talk about is why association does not imply causation. The best example I have of this is considering the two variables of number of popsicles sold in the summer versus number of shark attacks in the summer. Right. Typically, more popsicles are sold when more people are at the beach where they're selling popsicles. More people at the beach could lead to more shark attacks. However, even though there is a association between more popsicle sales and more shark attacks, selling popsicles does not cause more shark attacks. All right. So just because there's an association does not mean that we found causation. That's a whole other ballgame. All right. We're only talking about association here. Do not say that one causes the other. We don't have the information for that yet. All right. Is there anything I can clarify? Any questions? Okay. So then we're going to stop this one. And we're going to go to this one. All right, so in section 3.2, we're going to talk about least squares regression. All right, I've been talking about the line of best fit for a scatter plot. Now we're going to talk about how we actually get that line using our scatter plot data and how we make sure that we're getting the best line possible. So in this section, we're going to learn how to interpret the slope and y-intercept of a least squares regression line. Use the least squares regression line to predict y for a given x. Calculate and interpret residuals and their standard deviation. Explain the concept of least squares. Determine the equation of a least squares regression line using a variety of methods, mostly using our calculator. Construct and interpret residual plots to assess whether a linear model is appropriate. Assess how well the least squares regression line models the relationship between two variables, and describe how the slope, y-intercept, standard deviation of the residuals in R-squared are influenced by outliers. And we will get through like half of this lesson today. That'll be right. So here we go. Regression line is the first thing we're going to talk about. And this is essentially your line of best fit for your scatter plot. Right, linear, straight line, relationships between two quantitative variables are common and easy to understand. A regression line summarizes the relationship between two variables, but only in settings where one of the variables helps explain or predict the other. A regression line is a line that describes how a response variable y changes as an explanatory variable x changes. We often use a regression line to predict the value for y for a given value of x. All right, in this example here of the scatter plot with a regression line is based on the price or value of a Ford F-150 after a certain number of miles driven. Talking about like a used car. Okay. We'll use this example here for a little bit. A regression line is a model for the data, much like density curves. The equation of a regression line gives a compact mathematical description of what this model tells us about the relationship between the response variable y and the explanatory variable x. Suppose that y is a response variable plotted on the vertical axis, and x is an explanatory variable plotted on the horizontal axis. A regression line relating y to x has an equation of the form y hat equals a plus bx. It's basically the equation of a line. So instead of y equals mx plus b, we've kind of rearranged the letters just a tiny bit. In this equation, y hat is the predicted value of the response variable y for a given value of the explanatory variable x. It's a linear equation. As we've seen in previous math courses here, y equals mx plus b. As x changes, y changes. Y depends on x. Right. B is the slope. So instead of m, we're using b. The amount by which y is predicted to change when x increases by 1 unit. A is the y-intercept, the predicted value of y when x equals 0. Okay, so we're using different letters, right, than we have in previous math classes, but this is stats. They use their own letters. Does anyone need a moment to write anything down about the regression line? Here's an example on interpreting slope and y-intercept. The equation of the regression line is shown as price hat equals $38,257 minus 0.1629 times miles driven. We have the same scatter plot with regression line as we saw on the previous screen. Our problem here, identify the slope and y-intercept of the regression line and interpret each value in context. So our solution, the slope B equals negative 0.1629 tells us that the price of a used Ford F-150 is predicted to go down. It's a negative association. It's a negative slope. By $0.1629, 16.29 cents, for each additional mile that the truck has been driven. So as the miles increase, the value decreases. We have a negative association. The y-intercept A equals 38,257 is the predicted price of a Ford F-150 that has been driven 0 miles. So again, the parts of this behave exactly as we would expect them to in a normal linear equation. They're not doing anything different. We can use a regression line to predict the response y hat for a specific value of the explanatory variable x. We use the regression line to predict price for a Ford F-150 with 100,000 miles driven. So we have price hat equals 38,257 minus 0.1629 times miles driven. So we replace the miles driven with 100,000. We punch this through the calculator. And we get that the price, the predicted price for a Ford F-150 that is driven 100,000 miles is $21,967. Right, this is not saying that it is the price. This is the predicted price. We can use a regression line to predict the response y hat for a specific value of the explanatory variable x. The accuracy of the prediction depends on how much the data scatter about the line. While we can substitute any value of x into the equation of the regression line, we must exercise caution in making predictions outside the observed values of x. So it's kind of wise to say within the observed values, the observed possible values for your x explanatory variable. Going outside of those makes it a little more wishy-washy. Extrapolation is the use of a regression line for prediction far outside the interval of values of the explanatory variable x used to obtain the line. Such predictions are often not accurate. Don't make predictions using values of x that are much larger or much smaller than those that actually appear in your data. If they're close, it's probably okay. It could be pretty close. The farther away you get from your actual data set, the riskier it is to use your regression model. In most cases, no line will pass exactly through all the points in a scatter plot. A good regression line makes the vertical distances of the points from the line as small as possible. A residual is the difference between an observed value of the response variable and the value predicted by the regression line. So we see in our picture here, we have our regression line, we have all of our observed points, and then these vertical lines represent the distance from each point to the regression line. The residual is equal to our observed y value of the point minus the predicted y. In notation, we have y minus y hat. And that's essentially giving us the vertical distance between the point and the regression line. Different regression lines produce different residuals. The regression line we want is the one that minimizes the sum of the squared residuals. It's essentially the best fit line. The least squares regression line of y on x is the line that makes the sum of the squared residuals as small as possible. That was the linear regression command that we used in the calculator, that number 8 option. It's for the least squares regression line. And we have this kind of visual here of the squaring of each of the residuals. The sum of the squared residuals here is a really big number, but it's probably the best we can do, given the data. So then we use residual plots. One of the first principles of data analysis is to look for an overall pattern and for striking departures from the pattern. A regression line describes the overall pattern of a linear relationship between two variables. We see departures from this pattern by looking at the residuals. The residual plot is a scatter plot of the residuals against the explanatory variable. Residual plots help us assess how well a regression line fits the data. So here we have the same scatter plot with our miles driven versus price and our regression line drawn through the scatter plot. Here is the residual plot that has the 0 horizontal line here representing no distance between a point and the regression line. And then our scatter plot points here represent how far away each point is compared to the regression line. A residual plot magnifies the deviations of the points from the line, making it easier to see unusual observations and patterns. Right. The residual plot should show no obvious patterns, so it should just look like a big old scattering of points. And the residuals should be relatively small in size. These graphs here show patterns in the residuals, and the linear model is not appropriate. If we see on the left here, the residual plot shows this like nice parabola, and the linear model, the line of best fit here, is not a good match for our data because it is curved. It's obviously curved. So this is not the appropriate model. If a linear regression line is the appropriate model, then we should see a scattering of the points like we saw on the previous screen. There shouldn't be an obvious pattern. To assess how well the line fits all the data, we need to consider the residuals for each observation, not just one. Using these residuals, we can estimate the typical prediction error when using the least squares regression line. And this typical thing refers back to essentially standard deviation, where a standard deviation is the typical distance from the mean or expected value. Right? The linear regression line provides us an expected value for y, and we're now going to find the typical deviation from that. Right? If we use a least squares regression line to predict the values of a response variable y from an explanatory variable x, the standard deviation of the residuals, s, is given by, so we have s now. S is equal to the square root of the sum of the residuals squared divided by n minus 2, which is equal to the square root of the sum of yi minus y hat squared over n minus 2. Right. Again, please don't try to calculate this by hand. Right. We can get this value from our calculator. This value gives the approximate size of a typical prediction error or residual. So, as I said, we can get this in our calculator, and that's what you should do. Notice in the first thing that we did here, from our previous example in 3.1, we don't have s as one of our outputs. We have r and r squared, which r squared we'll get to shortly. But s was not an option here. But we do have the correct linear regression line. So what we need to do is we'll go to stat, and now we'll go to tests. Right. And if we use the linear regression t-test, which is actually something that it's a test that comes up in chapter 12 that we're not going to get into, but we can use the function here to get values that we need, right? It's this option here, linear regression t-test, option F. Right? And again, we'll use the same X and Y list that we used previously. So this is going back to the previous example we talked about with the SEC football teams and points scored versus wins. We need to change the frequency. We're not dealing with this row, the beta and P, phi, all that stuff. Don't worry about that. the regression equation we're using, right? So the thing that we're checking to see how far each point is away from is stored in Y1 still. That's where I had it stored from the previous one. So I have that equation already. So I've just told the calculator, hey, this is where the equation is, use that. Otherwise, I'd have to type in the equation. To get this Y1, if we're highlighted in here, you just go to vars, y bars, function, and select function Y1. It just goes in there. And then we'll tell it to calculate. Now I get a whole bunch of stuff. We're not going to worry about that. We don't need this t value right now or the p value. This all top part here is like a significance test for this, which we're not doing right now. We'll scroll down and we get our A, B, which we had. That's our A is our y-intercept, B is the slope. We have S, that's the one we wanted, 1.235. Right, so this value here is what we were concerned about that we wanted for this, which is the standard deviation of the residuals. Right. And again, since we already had the data input, or even if we had to input the data, it's going to be easier than trying to make sure we do this equation right. Right, so we will use the calculator. Is there any questions? I know this is a lot, and that's why we'll do examples tomorrow. Okay. So then we have the coefficient of determination. The standard deviation of the residuals gives us a numerical estimate of the average size of our prediction errors. There is another numerical quantity that tells us how well the least squares regression line predicts values of the response y. The coefficient of determination r squared is the fraction of the variation in the values of y that is accounted for by the least squares regression line of y on x. We can calculate r squared using the following formula. And again, r squared was already an output on our calculator. I do not recommend trying to do it by hand. Because again, this is 1 minus the sum of the residuals squared divided by the sum of the, basically the variances squared. The sum of the variance, basically, ish. Right? It's a mess. You don't want to try to do this by hand. Right, r squared tells us how much better the least squares regression line does at predicting values of y than simply guessing the mean y for each value in the data set. So it tells us how accurate of a predictor this is. So in section 3.1, we look at the relationship between the average number of points scored per game X and the number of wins Y for the 12 college football teams in the SEC conference. A scatter plot with the least squares regression line and a residual plot are shown. The equation of the least squares regression line is y hat equals negative 3.75 plus 0.437 X. Also, S is equal to 1.24 and R squared is 0.88. Calculate and interpret the residual for South Carolina, which scored 30.1 points per game and had 11 wins. The predicted amount of wins for South Carolina is y hat, which is negative 3.75 times 0.437 times 30.1 equals 9.4 wins. So based on that least squares regression line, we predicted that South Carolina would win 9.4 games. The residual for South Carolina is the actual number of games they won minus the expected. Right? Y minus y hat, which is 11 minus 9.4, we get 1.6 wins. We have a positive residual, which means that South Carolina won 1.6 more games than expected, based on the number of points they scored per game. So they did better than expected. B is a linear model, right, appropriate for these data. So we're going to look at the residual plot. We don't see any apparent pattern in the residual. And relative, everything is within about 2. It's within about 2 of the line, so it's not terribly spread out. Because there is no obvious pattern left over in the residual plot, linear model is appropriate. Right? That's good. That's all we need. There's no pattern. We're good. We want to interpret the value s equaling 1.24 when using the least squares regression line with x equaling points per game to predict y, the number of wins. We will typically be off by about 1.24 wins. It's kind of like our margin of error. And the value of r squared equaling 0.88 means that about 88% of the variation in wins is accounted for by the linear model relating wins to points per game. Means our predictions are pretty close. We have a pretty good regression line that does a good job of predicting how many wins. 88%, that's good. All right, and we're gonna stop here. The next thing we'll do tomorrow, which is something, yeah, that I've been told we definitely want to cover. All right, so where's my mouse? There. And there. All right, so good. That's what we're going to cover today as far as content is concerned. All right, we're going to cover the last part of 3.2 tomorrow and then look at examples on how these things work. I'm going to try to find examples using previous like FRQs and things so we can really see how this gets applied in a testing environment. Hopefully that's helpful. Hopefully it'll help make a little more sense of this stuff. So if you have any questions, comments, concerns, if you need help with anything, please make sure you're letting me know. Send me an email, send me a message, do something to let me know. I'm happy to help. Besides that, I hope you all have a great rest of your day, and I will see you all tomorrow.